Swayam Prabha. Digital India. Educated India.
Welcome back, students. In the last lecture, we looked at operational amplifier as a universal amplifier that we use to implement a variety of circuits. That's what we plan to do. And we looked at this operational amplifier as a black box. Now, in that lecture, we went through what were the characteristics we desired as an ideal operational amplifier. Today's lecture, we are going to put together a few circuits using an operational amplifier and really see. I think that will give you a motivation in terms of why this operational amplifier is so popular and useful. I'll try to use a few real-world examples while we are learning them, and hopefully that's exciting and interesting for you to learn. The first example we're going to go through is called inverting amplifier. So we'll start with an op-amp, and then we have a positive terminal and negative terminal of the op-amp, and then we will attach resistor like this, another resistor like this. Okay. Now, here is something that I would like you to remember, because otherwise you will get confused over and over again. The concept of analog ground and the DC ground. So as I explained earlier again, when we connect an external power supply to your circuit, then there is something called chassis ground or ground, DC ground. Okay. So for example, this particular amplifier, we could connect, this is plus 5 volts and this would be 0 volts. Okay, so we are used to calling this as ground, and the term ground is used quite loosely and interchangeably when people are designing circuits. And once you get used to it, you understand which one to use where. So I just want to explain this to you. So this would be 0 volts and this would be connected to your, let's say, I'm just going to draw it like this, and this would be connected to your supply, okay, which is coming from plus and minus. Okay, so this would be, let's say, 5 volt supply. All right, so this term, the 0 volts, is also called ground, okay, or system ground or chassis ground, something like that. However, there is another term we like to call analog ground. Okay, now concept of analog ground makes our life easy to analyze the circuit. So in this particular case, as I explained earlier, we would call a good number would be 2.5 volts. So I would apply plus minus 2.5 volts here, and that would be my, this we would call this as analog ground. The reason is that you have a supply voltage which is going from 0 to 5 volts, and we will have AC signal moving around, right? So what's the best way to fit the AC signal here? It would be like this. And in that particular case, this half supply voltage, which is 2.5 volts, it's very convenient for us to use it as a AC ground, 2.5 volts. So now every time if I keep showing you this 2.5 volts explicitly drawn, then the circuit diagram would get very complex and confusing, right? So what we say is we typically draw circuits for analysis. They are with AC ground. So what AC ground means is it's assumed that you have found some potential which is usable, like this one here, which is 2.5 volts over here, around which the AC signal is moving around. Okay, so you can also think of it as a convenient DC operating point for your amplifier. All right. Okay. So in this particular case, let's say I'm going to, I'm going to draw first an explicit circuit
about how this amplifier is going to look like, and then we will draw an AC circuit. So you can see how simple it becomes. So in this particular case, I have shown you this is the supply voltage which is going on this side. You are going to the AC 220 volts, right? And it's giving me this supply voltage. And on this side, I would apply something like an AC signal, VAC. And again on this side also, I would like to apply AC ground voltage, which is 2.5 volts. Okay, so this node again becomes AC ground for us. So we would operate this amplifier. If I have to draw all the sources explicit, it would look like this, and this output voltage will be also somewhere around this AC ground, and there'll be signal AC signal riding on it. All right. So this is a very explicit circuit that I have drawn with all the sources. When let's say you had to put together this circuit in the lab on a bench, this is what you would do. Okay, these are all the sources you would put in there, and you would take this. This is, let's say we talked about 741 amplifier, right? So this is what we would do, and this is I forgot to mention, this is your R2 and R1. All right, so this is a very explicit circuit. However, this is very cumbersome to draw every time. So we like to, as analog designers, we would like to simplify things with certain things assumed. And so I would simplify this schematic to something like this. And you can immediately see the difference. And we won't show supply voltage anymore. And here I would show, this is my AC ground, and then I would show VAC or VN. This is a AC source. Okay, so this is R1 and R2. So this is simplified circuit that we like to draw. Now let's analyze how does this circuit work step by step and understand what's the output is going to look like. And again, here in this particular case, the output would be plus minus with respect to minus will be with respect to AC ground. So this we are signifying as AC ground, or we also like to call it analog ground. Okay, so do not get confused between this and the 0 volt that you are applying from a DC power source. Okay, now how do we analyze this circuit? What have we learned so far? We know Kirchhoff's current law, voltage law, so all of you are used to that, so just use those. And I'm sure you already have figured out how to solve this, but let me take a few baby steps so that we start off with simple circuits. And this is the current I1 flowing through R1, and there is current I2 flowing through R2. Okay, note the direction of the current. So now what we can do is, we know that amplifier, this operational amplifier, we know it's AC circuit or a small signal behavior circuit, right? So that is like this. You have Vn, which is negative terminal, and Vp, which is a positive terminal, and there is no current. The current going inside the amplifier is 0, I. There's no current flowing inside the amplifier, and the simplest model that we have created is the following, where we have plus minus AV and Vp minus Vn. That is our small signal model. All right, and this is your V out. So let me see if I can draw an amplifier on top of it so that it will be clearer. Something like this, something like this. All right, and now we are connecting a resistor here this way and another resistor over here this way, and then I am applying a AC voltage source called Vin over here, and Vp I have connected to analog ground. Right, so R1 and R2. Now, as already given by this expression, we know that output V out is equal to AV times Vp minus Vn. Okay, so Vp minus Vn is equal to V out divided by AV. Now, what is the property I taught you for the ideal operational amplifier? We say that AV is very large, okay? And very large means it could be a million or things like that. So the voltage V out by definition is going to be between 0 volts and is going to range between 0 to VDD. If you divide that by a million, you're going to say that, hey, Vp minus Vn is almost equal to 0. Okay, 0, and that tells us Vp is equal to Vn. So this is an important property of op-amp based circuits in a negative feedback. Okay, again remember we are connecting the feedback in this fashion, and what this does is due to this property, even though the two nodes Vp and Vn are not connected together, it appears that there is a short between node Vp and node Vn due to negative feedback. Okay. So we call this, also we can, since this particular node is grounded, we also call that as a virtual ground appearing on the other side. Okay, so you can, there are two terminologies I'm going to tell: virtual short, because there is no physical short between Vp and Vn. However, Vp is equal to Vn, so we call it virtual short between Vp and Vn. Okay. So and other terminology is we say there is a virtual ground at Vn because Vp is connected to 0, is connected to ground. Okay, so Vp is connected to AC ground, and as a result of which Vn becomes a virtual ground. Okay, so this is a terminology that you have to get familiar with and get used to it, and that's why I'm going through it in so much detail. Okay. Now we can apply KCL at this node. Let me use a different color at this node. And what does the KCL tell you? The KCL will tell you I1 is equal to I2. And what is I1? So I1 is equal to I2 is our KCL. Okay, and I1 is equal to, what is I1? I1 is equal to Vin minus 0. Why am I using this 0? Because this is connected to analog ground or a 0, and as a result of which the negative terminal also became virtual ground. So Vn minus 0 divided by R1 and is equal to, that is equal to 0 minus V out divided by R2. So that is the equation that we have to use. All right. It's important to note the direction of the current whenever you're using your KCLs, KVLs, Ohm's law. Just make sure that you don't make a mistake, one silly mistake, and you will get a totally wrong answer. So make sure you get the flow of the current and the potential difference always in the correct direction. All right. So if this, with these two equations, you can easily convince yourself that V out divided by V in is equal to minus R2 divided by R1. All right. So this is our final equation. Here the negative sign shows it's a inverting amplifier. Inverting amplifier, this particular term is called closed loop gain. So when you just take an amplifier, operational amplifier, then the model that we have created over here, this is an open loop configuration, right? The AV gain is open loop gain when it's not hooked up. And when you put the amplifier in a circuit with proper feedback, this becomes closed loop gain. Okay. As you can see, the final expression doesn't contain anything to do with AV. Okay. It only contains R2 and R1. So it's a ratio of resistors. So this way of doing amplification is very popular even in integrated circuits because there we can, we may not be able to get exact value for each resistor, absolute value. Meaning if I choose a value of 1 kilo ohm on a chip, then I may get maybe 900 ohms or I may get 1.1 kilo ohm. However, if I draw two resistors next to each other, then both those resistors will track each other really well, almost as good as 0.1%. If you do the layout part properly, if you draw the resistors very well in an integrated circuit fashion, then you can get excellent matching between the two. As a result of which, you can see that R2 and R1, if they are drawn appropriately, then they match very well with each other. So the absolute value of R1 and R2 may change, however, they will move together on each chip if they are physically next to each other. So what happens then is we get a very accurate, even though each component, for example, R1 may vary plus minus 15%, R2 may vary plus minus 15% from its desired value, and AV can vary, a lot. I mean, it can vary 50% or whatever. It doesn't make a dent into our equation, okay, as long as AV is large. So that's the reason operational amplifier is very popular, because I can get accurate gain even though the amplifier by itself does not have accurate gain, as long as AV is large, okay. So as a next follow-up, what we will do is we will figure out effect of finite open loop gain. So that's our next. All right. So if you remember, V out is equal to AV times Vp minus Vn. Now we will keep this term AV. We will not make any approximations, and we'll figure out what's going on. All right. So in this particular case, we know that we have connected the positive terminal Vp to 0. So we can say that, hey, this is Vp is equal to 0. So V out is equal to minus AV times Vn. Now going back to the equation, let me redraw the circuit here so that you can reference it while you're doing this. So the equation will become now V in minus Vn divided by R1. So this would be the current flowing this way is equal to the current flowing this way. So why is I1 is equal to I2? Because the op-amp is ideal and there is no current flowing inside the op-amp. That's the property of the op-amp, ideal op-amp, right? Okay. So we would get V in minus Vn divided by R1 is equal to Vn minus V out divided by R2. Now we can substitute the Vn value from here, and we will get V in plus V out divided by AV divided by R1 is equal to minus V out divided by AV minus. So I'll let you do this math, and the final result will be gain. Again, what kind of gain is this? This is closed loop. Gain is equal to V out divided by V in is equal to minus R2 divided by R1 divided by 1 plus R2 divided by R1 and divided by 1 divided by AV. Okay. So it's important that you go through the math yourself and convince yourself with this answer. Sanity check. Let's say this AV is very large, then what will happen? The denominator will become 0. The denominator will become equal to 1 because this term will go to 0. Okay. And then again we get the answer which we originally got, which is 1 divided by what we got was minus R2 divided by R1. So just to clarify again, we have to make sure that 1 plus R2 divided by R1. So AV has to be much larger than 1 plus R2 divided by R1. That's only time when we can make this equation true. Okay, so this will keep gain G independent of AV, the op-amp's open loop gain. All right, let's take one example so that we can convince ourselves with this. So let's take an example with resistor R1 is equal to 500 ohms, and then resistor R2 is equal to 20k ohms. So desired gain would be G is equal to minus R2 divided by R1, which is equal to 20k divided by 0.5k, and that is equal to minus 40. Again, minus being inverting amplifier. So we will figure out value of the gain, closed loop gain, G. If we substitute the value AV here equal to, let's say, 1000. We'll try two numbers, 1000 and also we'll try 1 million, 10 to the power 6. Okay, and then we will see what happens to the value of the gain. So the gain G is equal to R2 divided by R1. I'm going to do mod of gain 1 plus R2 divided by R1, 1 plus and 1 over AV. So here you can say R2 divided by R1 is 40 divided by 1 plus 41 divided by AV. So if we substitute for AV, let's say we substitute 1000 and we substitute 10 to the power 6. I would take a pause here, use your calculator and tell me what the value of effective gain is. You can also pause the video and you can write the expression and then you can start the video. So when AV is equal to 1000, as you can see, the gain would be 38.424. So pretty close to 40, not too far off. However, when we get gain of 10 to the power 6 or a million, the gain becomes 39.9984. So we are closely approaching the desired value of 40 as the gain AV keeps increasing. Okay. Now the interesting part is, let's say this gain, as I said, we just want the gain of the amplifier, the open loop gain of the amplifier, operational amplifier, to be large, very large. But we don't need it to be accurate. So for that matter, the gain of the amplifier could be 1 million or half a million. That doesn't matter, but it has to be large. And let's say we substitute, instead of 1 million, we substitute half a million, 10 to the power 6. So this is a large error, right? This is 50% or 100% error in terms of accuracy of the gain. However, we can substitute here and you can see that with half a million, the gain becomes 39.9967. So when you compare these two numbers, you can say that, hey, there is a negligible change. Even when the gain AV is just large, it's not accurate. And that's the beauty of operational amplifier. We can create circuits which have accurate responses using an operational amplifier which doesn't have accurate gain, exact gain. Okay. So the closed loop gain, the key insight here is closed loop gain is insensitive to variation in open loop gain of amplifier, op-amp. Okay. Next example we're going to go through is a very interesting example, so pay attention. So many of you must have attended concerts, or for folks in IT, we have our annual festival Mood Indigo, and you must have observed that there is this person who's operating this big box with whole bunch of knobs. And I mean, it kind of looks like this. Let me show you. I mean, I'm just showing you top view, and it has whole bunch of knobs like this, and there some kind of things that you move up and down. Okay. And this person who's operating this box is one of the most powerful person in that concert. What he or she is doing is controlling the sound from each microphone which is on the stage. So the job of this person is to make sure that the final audio that you hear is is really perfect, meaning only when somebody is speaking that particular microphone is enabled. And if it's creation of music, then there is a lead vocalist, there is a male vocalist, there is a female vocalist, there is a tabla player, there is a guitar player, all those things, right? All these people are playing their instrument. And so this person is sitting at this table right in the middle. On the he or she has the best view of the concert, and they are controlling the whole show, and they're controlling what you're actually listening to. And they are operating something called audio mixer. And we are going to learn what this circuit looks like, again using a quite so simple operational amplifier that we just learned. Okay, let's draw the circuit of this audio mixer. Minus, plus, and this is our analog ground, and there is a feedback. And since the output is being fed back to the negative terminal, it's a negative feedback. Let's call this RF feedback. Okay, now at this point there are, let's say, whole bunch of different resistors which are connected. In this particular example we will just use 3, or maybe let's draw n, and let's call this R1, R2, all the way to Rn. Now V1, V2 and Vn, and this is our output Vout, referred to analog ground, plus minus. Okay, and let's say that there is current I1 flowing here, I2 flowing here, and In flowing here, and the current going in this resistor RF is IF. Now if I apply Kirchhoff's current law at this node, then you can see that we can write an equation: I1 plus I2 plus I3 plus blah 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 plus In is equal to IF. The current entering the node and leaving the node has to be the same. So we can then write equation V1 divided by R1. Again, why didn't I do V1 minus Vn? Vp is already 0, and because of negative feedback, this node Vn is virtual ground. Hence I am just saying V1 minus 0 divided by R1. And now that we got used to it, I'm just going to drop this 0 term for ease of analysis. Okay, so V1 divided by R1 plus V2 divided by R2 plus we go all the way to Vn divided by Rn is equal to minus Vo divided by Rf. So this will give you output voltage Vo is equal to minus Rf divided by R1 times V1 plus Rf divided by R2 times V2 plus Rn times Vn. So as I said, if I want to, if the music is, people in the back are complaining they can't hear it, then our audio engineer would just change this resistor RF, and he or she would increase the resistance RF, and generally what you see is there are two types of pots. It's called pot. Pot means potentiometer. One is one looks like this, where like this, and there is a center terminal, and there is this terminal. So by physically moving this brush around this way or that way, we can increase or decrease the resistance. And these are the pots. There are beautiful buttons, metallic buttons that they put it so that it's easy for them to operate.